Hello. Now we shall do some examples where I want to show you how to approach different types of series. Strategy for testing series. We are testing series for convergence. Up to now, we know how to evaluate exactly only geometric series and some very simple telescoping series. In general, we just want to know is the series convergent or not. Okay, suppose you have this series. Sigma n goes from 2 to infinity, n minus 1, n cubed plus 1. This series includes some constants, plus 1, minus 1, and our experience from the section on comparison test shows that the best approach here is to just ignore these constants, just cross them out. So this series will be similar to the series n on top and cubed below. So what we're just doing, we're removing these constants. They're not growing, they don't change the behavior of the series. Okay, so our series is similar to this. Here we can reduce by n, and this is the series 1 over n squared, which is convergent. It's a p-series where p is equals to. Well, it's good to know that the series that we have here is quite popular in mathematics. In this example, I studied summation from 2, but if we write the summation here from 1 to infinity, the value of this series can be computed. It's pi squared over 6. It's an interesting result, which was obtained by Euler centuries ago. Anyway, so this series we should compare to convergent p-series because we have powers of n, and this is the best way to go. If you think about other tests like integral test, it's not appropriate. If you take ratio, it's not appropriate because, as I told you before, series which look like p-series cannot be tested successfully with the ratio test because they bring to this case the inconclusive case. The series is also not alternating, so we practically have no other choice. Anyway, another example. Look at this. Now, alternating series. We have on the top n fourth power, and below we have 4 power n, starting from 1 to infinity. So it's one alternating series, and then looking carefully at the positive factor here, which we call b sub n, we see n fourth power on top, 4n power below. Well, we know that the exponential function grows faster than any power function. So again, experience that we have from before says that most likely this series will be very well convergent, and it's appropriate to test immediately for absolute convergence because this general term behaves very well. So let's take absolute value of a sub n. A sub n is this entire expression. So a sub n here is negative 1 n minus 1 and fourth power over 4 power n. Absolute value of a sub n, we have to remove the alternating factor. It will be this positive factor. This is b sub n. And now, when you have such exponentials, a ratio test is appropriate. think about ratio test. The root test also will work here. Now I will show you later. But let's do first the ratio test. So we take an plus 1 over an with absolute values. Here I'm writing an plus 1. And multiply by the reciprocal of an absolute value. So 4 power n is on top now. Here n fourth power. So we can rearrange this way. 4 power n over 4n plus first. You see I put similar factors one above the other. And here n plus 1 over n, I can unite like that, fourth power. Reducing by 4nth power, this will be 1/4. And inside the parentheses I can write 1 plus 1nth dividing by n, fourth power. And this has a limit. The limit is 1/4 times 1. And the expression in the parentheses approach is 1. 1/4 power is 1. So the final limit is 1/4, which is less than 1. And the ratio test says that the series is absolutely convergent. Absolutely convergent by ratio test. I want to repeat again that every time when we test a series, it's not sufficient just to say convergent or divergent. We have to explain because of what test. What test gives the result. Going to the next example, we have this series n squared exponential negative n cubed, starting from 1 to infinity. Such a strange series we have seen before with the integral test. So we again think about integral test. N squared exponential negative n cubed extends to x squared exponential negative x cubed. So we need to take this integral from 1 to infinity, x squared exponential negative x cubed dx, and see is this convergent or not. And here obviously we have to make a substitution. For example, I can take x cubed to be a new variable, u equals x cubed, du will be 3x squared dx. X squared dx will be 1/3 du. So this product appears in the integral. And the limits are the same. When x is 1, u is 1. When x goes to infinity, u goes to infinity. So what we have, 1/3 in front. I'm writing exponential negative u du. We can integrate exponential easily. So this exponential negative u over negative 1 to infinity. And let's write negative 1/3 in front. And here we have limit exponential negative u when u goes to infinity minus exponential negative first power. And about the limit, we don't care about the exact value of the integral because we just need to know convergence or divergence. The value of the integral is not the same like the value of the series, so we don't need to compute it completely. Just look at this limit. If the limit exists, the integral is convergent. So here is this limit again. U goes to infinity. I can write this like limit 1 over e to the u goes to infinity. We have seen this many, many times. The limit is 0. Okay, so the conclusion is this. Series converges by integral test. Integral test. Let's write test better. integral test. Okay, going to the next example. The next example is this series here, 1 over k square root k squared plus 1. That's how it's written. I took it from the book. K is the index here. It goes from 1 to infinity. How to do with this series? It looks somewhat like our first example. There are powers of k. And there is a root, of course. The denominator goes to infinity, so the general term goes to 0. This is fine. And what we're going to do is compare again. I shall drop this term here, drop this, and then let's see what remains. So this will be similar to the series 1 over k square root of k squared, which is actually 1 over k squared, k times k. This is just k. And again, we have this series which we had before, a convergence series. And we can remember the value of the series is pi squared over 6. So this series requires comparison test. Next example, we have sine 2n divided by 1 plus 2 power n, and from 1 to infinity. How to approach this series? What to do with this sign on the top? Well, the sine and the cosine, which we have seen before, they have a restricted range. Sine 2n, no matter what is n, in absolute value is less or equal to 1. So this series is appropriate to test again with the comparison series, with the comparison test, in the following way. I shall take the general term, a sub n in absolute value. This is sine 2n in absolute value over 1 plus 2 power n. We don't need absolute value for the denominator, it's positive. And this will be less or equal 1 over 1 plus 2 power n. So I'm reasoning this way. 1 over 1 plus 2 power n possibly gives you a term of convergent series because it very much looks like a geometric series. So most likely our series will be absolutely convergent. So if you look at the series with absolute values here, this will be less or equal to the series 1 over 1 plus 2 power n. And now we can drop this constant 1 again. And the resulting series is similar to 1 over 2 power n, which we write 1/2 power n. And this is a convergent geometric series. Convergent geometric series. And we're not computing, the series is not important to know the value. The comparison test here works very well. I'm using this form of the comparison test. If a sub n is non-negative and less or equal b sub n, and the series for every n, the series b sub n converges, then the series a sub n converges. Here above I have absolute value, so talking about the positive terms. So this is the test that I'm using. Now look at the next example. We have series n times sine 1 over n. N goes from 1 to infinity. Again, this sign. This time I'm not estimating the sign. It doesn't give you anything. If you take absolute value of this sign that less or equal to 1, it doesn't help. You'll get the divergent series because of this factor n. What we need to do is look more carefully at the general term, a sub n. A sub n is n sine 1 over n. And this is an undetermined product. Let me write better this equality sign here. It's one undetermined product. N grows to infinity. 1 over n approaches 0. Sine of 0 is 0. So we have such undetermined form. I can reason this way. This extends to x sine 1 over x when x grows to infinity. And I can write limit a sub n equals limit when x grows to infinity, x sine 1 over x. And we have seen such things before. The way to do it, from undetermined product, I shall write the ratio of, I shall write this ratio, undetermined ratio, sine 1 over x over 1 over x. So we see how we rearrange this product. X grows to infinity. When x grows to infinity, 1 over x approaches 0. So if you set t equals 1 over x, this limit will be sine t over t when t approaches 0. This limit is familiar from Calc 1, it's 1. You can use L'Hopital, or you can just remember what you did in Calc 1. So what we found here, that the general term a sub n approaches 1. This is different from 0, and we can use the divergence test. The divergence test says the series is divergent. The general term does not approach 0. So our series is divergent by divergence test. So every time when you have a series, it's good to look carefully at the general term and try to use intuition or some simple computation to see, is the general term approaching 0 or not? If it does not approach 0, the series is divergent. If the general term approaches 0, it doesn't mean it's convergent. Then you have to do something else, another test. Moving further, here is the next example. Series, here n squared plus 1 on top, 5 power n below, n from 1 to infinity. Well, we have seen something similar above. We can drop this constant 1 and use comparison test. We can compare to the similar series n squared over 5 power n. We have power function, exponential function, and the previous example shows that ratio test will be most appropriate. So here I can write this ratio an plus 1 over an. No need of absolute value. These things are positive. So I'm testing the simplified series, which I will show you is convergent. Then by the comparison test, the original one will be convergent. Now look again at this ratio. I'm writing an plus 1, so n plus 1 squared over 5 power n plus 1 times here an in the denominator, so this goes up. We did something very similar before, and again rearranging this way. And reducing by 5 power n. This will be 1/5, and here 1 plus 1/n squared, which approaches 1/5, because in the parentheses the quantity approaches 1. 1 squared is 1. This limit is less than 1, and our series is convergent. Convergent by ratio test. The original series then also is convergent by the comparison test. So the simplified series we tested with the ratio test, original series convergent by the comparison test. And is convergent by the comparison test. Now, we don't have to say it's absolutely convergent, because the series has positive terms. Here is the last example for today. We have such a strange series. On top, exponential power 1n, and below n squared, and from 1 to infinity. How to approach this series? Integral test can be used. Yeah, it can be used, but is it... we can use integral test, but there is something simpler. If we look more carefully at the general term, what is this exponential 1/n power? That's nth root of e. E is always a number which is approximately 2.7. If you take nth roots, it gets smaller. Anyway, this will be less or equal than 3. So the general term here is less or equal 3 over n squared. And this is general term of unconvergent series. The series with general term 3 over n squared, you can write 3 in front. And again, this convergent series which we saw before, it's convergent. So by the comparison test, the series A sub n is convergent by comparison test. It's dominated by one convergent series. All series here have positive terms, so this works very well. You can see how some simple knowledge about the Euler number can help you test this series, and you don't need to write integrals here. Why I mentioned the integral test? Because we used it several times for series involving exponential function. Okay, I think these examples are sufficient. More examples from the homework will give you better understanding. I'm stopping here, and our next subject will be power series, which we shall do next week. Goodbye.